So you might wonder why we are using pseudo-residuals. Why we are using pseudo-residuals, and why did we come up with this whole concept of the pseudo-residual, which is derivative of derivative of the loss function with respect to fk of x. Because we argued that in the discussion section of this video, we argued that the pseudo-residual is same or similar to a residual or error. And hence, I might build my model instead of building it on residuals, I might build it on pseudo-residuals. While that is a simplifying argument, remember this is actually a simplifying, this is a simplifying and easy argument. The more fundamental mathematical reasoning is slightly deep. Okay, so in this video, I'll try to explain why we even started using pseudo-residuals. What is the more fundamental or mathematical, what is the more fundamentally mathematical reasoning for using pseudo-residuals, right? Why can't we just simply use the residual and train a model on it? So let's go step by step. Okay, there is a very neat mathematical argument to it, and I'll go step by step. This is slightly involved mathematically. So again, this video is optional. If this is too hard for you, just skip it. You don't require to know the proofs. This is not exactly a rigorous proof, but it is like a proof, like a very strong mathematical argument on why we are using pseudo-residuals. Okay, let's go step by step. Okay, so there is this whole area in machine learning called empirical risk minimization, right? Which is the underlying mathematical concepts for in the whole of statistical machine learning. So there is an area called statistical machine learning, which tries to rigorously analyze algorithms, right? So empirical risk minimization is one framework to do that. Very, very popular framework. So without going too deep into the math for it, I'll try to explain you the core idea, right? So what is your goal? What is your goal? You're given a loss function. Let's understand it, right? You're given a loss function. So let's ignore, like, I'll only cover the most useful and most important concepts here. There is a lot of math if I go deeper. I don't want to overwhelm you with math, but I want to give you the nice intuition on what's happening, right? You're given a data set. You're given a data set of xi, yi's. You're also given a loss function, and you are asked to find a function f that maps xi's to yi's, right? That maps xi's to yi's, which minimizes the loss function, right? This is the broad goal of your supervised learning, whether it is regression or classification, right? So let's go into the specifics of the math. So in boosting, we know we want to build a sequence of models, right? We want to build a sequence of models. So given a loss function, right? Given a loss function, my first step would be that I want to find, so look at this, I'm given a loss function, right? My first function f0 of x is, I want to find a gamma here. I want to find a gamma here, which is a constant, right? Which minimizes my yi, which minimizes the loss function between a yi and gamma. Okay, let's assume my loss function is squared loss, right? So what am I trying to do? I'm trying to say, find a gamma for me that minimizes yi minus gamma squared. I equals to 1 to n, 1 by n. I want to find a gamma that minimizes this. This is what I'm trying to solve as part of my f0 of x calculation, right? So you can easily see in the case of regression, this gamma would be the average value of yi's. Okay, I will not go into the proof of it, but you can easily show that with optimization. Okay, so first you trained your base model. This is your f0 of x. Now, see, remember how do we want to build our models? Our model fm of x at mth step, right? Our function that we get is the sum of function that we got at m minus 1th step, right? Because I already have a function at m minus 1th step. So f of 1x at first step is equal to f0 of x plus something, right? That's what I want to do, right? So my f0 of x is defined very simply, but fm of x is equal to fm minus 1 of x plus, I want to, now this is the most critical part. I'll explain each piece slowly. Imagine you have a set H of all base learners, So if H is basically an example of set of all base learners, set of all base learners could be set of all decision trees. It's a massive set. It's a very, very large set, right? So imagine if I have a set H of all the base learners, because I already have F. Okay, let me zoom this in a little more so that I can go into the details of this. Okay, so let me explain this equation first, because this is very, very important. Your fmx is sum of the model that you got at fm minus 1x plus, right? You want to find a model at hm. This is the model that you have at the mth step. And this model should belong to the set of all the models. This is basically set of all base learners. Set of all base learners. So you want to find a base learner hm from the set of all the base learners that minimizes, remember, that minimizes the loss function. So what should it minimize? It should minimize the loss function given yi. And what is your new, what will be your new function, what will be your new yi hat? This is your yi hat, right? Your new yi hat. See, this is a very common way, right? You have your loss between yi and yi hat. And this loss function can be anything. It could be squared loss, it could be log loss, it could be one of the many, many losses that are used in machine learning, right? It could be your hinge loss, right? Any loss. Now comes the fun part, right? So let me read this again. Okay. So your model at mth step is the sum of model that you had at m minus 1th step, and you want to find a model hm from the set of all the models you have, which minimizes your yi, given that your yi hat, you're defining your new yi hat as the sum of the old model that you have plus hm. This hm is what you're trying to find here, right? Very, very simple. This is straightforward. See, this will get slightly mathematical, but please bear with me, right? So again, I'll repeat this just for clarity. Your model at mth step is the sum of the model that you get at minus 1 step plus the model at mth step, which minimizes, and you can pick this model from the set of all the models, set of all the base learners that are possible. Pick that base learner, pick that hm, which minimizes the loss with respect to yi. So this is your yi and yi hat, right? Your loss function, where your yi hat is the sum of your model at m minus 1th step plus the model that you found here. Now, while this problem is, you can think of this as an optimization problem. You can think of this as an optimization problem. While this is an optimization problem, there's a big issue here. Solving this problem is computationally infeasible, as it is mentioned here. It is almost impossible. Because look at it, your set H is a set of all all decision trees. Well, theoretically, like from a pure mathematical standpoint, this is cool. How do you actually solve it? Right? You can't try every HM here. You can't try every possible decision tree because there are infinitely many decision trees. Right? There are many, 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 many decision trees. You can't try all of them. So people said, okay, since this optimization problem is almost computationally infeasible, can we solve it using a hack? Can we take an approximation? Can we somehow take a approximation, or can we simplify it? While we're not solving this exact optimization problem, can we somehow simplify it for our own simplicity? Right? Remember, in the whole of optimization, when W was a variable, we said W new was equal to W old minus some learning rate and derivative of L with respect to W at W old. This is the core update step, right? This is the core update step in all optimization. While this is the older W, remember W here is a variable. W here is a variable like weights in logistic regression or linear regression. This is your learning rate, right? This is your learning rate, and this is the gradient, right? This is the gradient, right? While w here is a variable, right? This is your standard update step in all of gradient descent, right? This is the core idea in whole of gradient descent that we discussed in the linear regression and optimization chapter. This is one of the most important equations in whole of machine learning, probably your update step in gradient descent. Now, instead of your w's being variables, if your w's are functions, if your w's are functions, there is a lot of mathematical theory where instead of optimizing over variables, you can also optimize over functions, right? Of course, there are some mathematical constraints on it. So without going too much into the mathematics of optimization over functions, because I don't want to go into real analysis and things like that, right? Which is like a semester long subject. Without going into the details of it, let me simplify it for you. Okay, so I can write. So since this is a problem that I want to solve, I would say, right? I will use this core idea of an update step in gradient descent, and I'll apply something called the steepest descent. Let me explain what steepest descent does. It's exactly like gradient descent. So what it says is this, because this is what I want to solve, right? This is what I want to solve. Think about this. This looks like your W new. This looks like your W new. This looks like your W old. This looks like your learning rate, sort of, and this is your derivative that you have. Okay, so if you want to reimagine this step, this is inspired, right? This is inspired from W new equals to W old minus eta times derivative of loss function with respect to W at W old. This looks very similar to this. This is your new W, right? I'm just trying to compare this equation to this equation because we are just using the same update concept. We are using the concept of gradient descent here, right? To solve this optimization problem or to find an approximate solution to this optimization problem. So we are saying, right, fm of x is equal to, which is your new W is equal to old W minus some learning rate. And look at this, this is the grad, right? This grad is basically an extension to partial derivatives. It's derivative of L with respect to fm minus 1 fx. Okay, this can be written as this. Okay, so let me write this down properly. This derivative can be written as derivative of L with respect to fk of x at fm minus 1 x, because the derivative has to compute it at some point, right? So this is a big leap for you. But in mathematics, people have always used in the place of variables, they've used functions. Okay, I don't want to go into the mathematical theory, but this is the core concept, right? Now the big question here is, this is your update step, right? Now, how do you compute this? See, you have to compute this, right? There are two steps here. You know this, and you want to compute this. To compute this, you need a gamma m, and you need to compute this. These are the two steps. So since one way to compute this, as we'll see in the actual algorithm. So we'll go through the actual algorithm, which is just right below here, which is actually right below here. We'll understand the actual algorithm of gradient boosting in just the next video. But before we go there, the tasks we have are these, right? The first is, how do you estimate your gamma m? And how do you find this? Right, look at this. Your negative of grad of L with respect to fm minus 1 is nothing but your pseudo-residual. Right, this term, if you take the minus here, this is nothing but your pseudo-residual, because this is nothing but dl by dfx. Okay, or at kth step or nth step, whatever you want to use the step notation to be, right? So this is basically the partial derivative, and this is the grad notation to it. So what you get here, this gamma m, ignore the gamma m, if you ignore the gamma m, this negative sign and this grad that you have, the grad of L, right, together they form your pseudo-residuals. And this gamma m can be found very easily through a simple search or through a simple optimization problem again. which is called a line search, right? So this is the more fundamental mathematical reasoning on why we use pseudo-residuals, right? We don't use pseudo-residuals. We don't use pseudo-residuals because they're very similar to residuals. We use pseudo-residuals because there is a fundamental mathematical proof behind gradient boosting, okay, which follows this core concept that I just discussed right now. Again, please note that I'm not proving things very rigorously. There is a lot of hand waving that I'm doing here, but I wanted to show you why we use pseudo-residuals in the first place. In the next video, we'll actually go through the gradient boosting algorithm. We'll actually go through this step by step, where these two things will again come into play, where we will learn how to actually find this. Actually, we'll find this. I'll tell you the reasoning. We'll find this by fitting a model on this, by fitting a model on this, by fitting a model on pseudo-residuals, right? And we'll find gamma m by solving a simple one-dimensional optimization problem. Again, you'll learn the details of the algorithm in the next video itself, in this chapter, but the fundamental reasoning on using pseudo-residuals comes from pure calculus, comes from the core concepts in empirical risk minimization. And again, remember, this optimization problem is infeasible. This optimization problem is infeasible. So we have taken an approximation algorithm that we are solving using simple ideas in calculus and gradient descent.